Hello everybody and welcome to the latest edition of the Physics Corner, a series of videos in which we introduce simple physics problems and how to solve them. I'm your host, Dr. Christopher Sorolla. Today's question involves hearing. Specifically, how sensitive is an adult's hearing? Even more specifically, at what frequencies or pitches of sound are we the most sensitive? So we can answer this in round terms if we use physics. Now, if you want the real details on human hearing, of course, you should go to an audiologist or a doctor who specializes in human hearing. But it's interesting in that physics can tell you some very basic ideas, some rounded off numbers, if you will, about what's possible. So, a typical adult has an ear canal about 2.5 centimeters deep. Again, of course, it varies from person to person, as it will, but that's a pretty round number. And that fact alone helps us understand why people hear with the particular sensitivity to pitch that they hear. So we can do this. We can model the ear canal of a person as an open tube at one end and closed at the other. So this would be the opening to air, and deep inside is the end of it is the eardrum, and that makes a closed end. Now, yes, I'm aware that the shape of it is not perfectly smooth like this. I drew it as a cylinder, but the general aspects are what we care about here. And it does give us some pretty good round numbers for what we're talking about. Okay, so why does this matter? Well, let's think about this. If a sound wave, or any wave for that matter, but if a sound wave enters into the ear, it's going to run into the back end over here. Now, if it runs into the back end and it doesn't hit it in the right spot, so to speak, or it's the wrong wavelength, if you will, those wavelengths will be destructively interfered with. They will tend to cancel each other out. However, if you have a wavelength that is just the right size, it will be reinforced by the hearing. Now, it's not an all or nothing deal. I should emphasize, obviously we can hear at many pitches, not just one or just a few pitches. We hear sounds of all different frequencies, right? But this is going to emphasize or really gather together the one real possible wavelength that you can hear best at. So how might we kind of sketch this out or understand how it's going to happen? So let me sketch in a little midline here for the moment. Kind of get a little bit of a physical appreciation from what will happen like that. Now, suppose we have a wave of sound that enters into the ear and it hits exactly at this point right there. Now, by the way, I should mention this, it doesn't matter that the sound waves are what we call longitudinal waves, which is sort of accordion-like, if you will, and other kinds of waves are transverse waves that go up and down, like, say, waves in water. For our purposes, the mathematics ends up being the same. So I'll draw a picture for one kind of wave that's not really super representative of what a sound wave is, but it doesn't matter for the math. So this is a little bit easier to see it when I do it this way. Anyway, suppose that happens. Now, if a wave were to, say, wavelength were to hit here or here, there'll be destructive interference, at least to some extent, and the wave won't be, say, exaggerated or enhanced as much as it can be. So we want to be right there. By the same token, if the wave reaches this point here, or this point for that matter, on the edge of the ear canal, then again, it'll tend to be enhanced. If it shows up at some other position over here, say in between somewhere, again, there'll be at least some destructive interference. So if we want the most sensitive possible wave, we want a wave that we can sketch, for example, something like this. Okay. Now, notice I've only sketched in part of a wave. If we were to continue sketching the wave, of course, it will look something like this, won't it? So if we look at some of these major points in here, like that, notice I've gone 1, 2, 3, 4, if you will, times the whole length of the wave. In other words, there's a quarter of a wave fitting in here. So if I say that the length of the ear canal is this, then the wavelength that fits in best to give us the best sensitivity, which we call lambda naught, will be 4 times the length of that canal. Now, just for comparison's sake, and we did have a video to this extent, if we were to have a slightly different situation, if, for example, we had openings at both ends, or we had closures at both ends, either one of those would work, then it turns out that the best wavelength to fit will be twice the length of the opening or the string or whatever you have in there. But this isn't that case. This is one end open, one end closed, and we get a quarter wavelength is the best fit, right? So I already said it, the depth of the canal is 2.5 centimeters. So let's write that down. Or we were going to want to put this into meters, 0.025 meters, like that. The speed of sound in air, and this is a wave in air, mind you, will round off to 343 meters per second. Now, that's also worth a very quick mention that this is also kind of a rounded off or average number, that the speed of sound in air can go up or down a little bit depending upon the density of the air, the temperature of the air, things like that. But it's not going to deviate by much, and this is a pretty good result for what we have. Okay. So what we're after then ultimately is the fundamental frequency, okay? The frequency or pitch at which we can best hear the sound waves. All right, so what does that give us? So the fundamental wavelength is simply 4 times the length of the canal, so 4 times 2.5 centimeters, which of course is 10 centimeters, or approximately 0.1 meter, like that, of course, right? And then, what's the relationship between frequency, wavelength, and wave speed? It's simply this, and I could put the knots in there if we prefer to keep them there. By the way, if you do put the knots on one, you have to put the knot on the other, so if I've got a fundamental frequency, fundamental wavelength, don't mix and match. All right, solve for fundamental frequency like that. So speed divided by fundamental wavelength. And we get 343 meters per second divided by 0.1 meter, or 430 hertz. And that, therefore, stands for the frequency at which an adult human, average adult human with average hearing, so we're not talking any strange physical problems, we're not talking any illnesses, for example, or loss of hearing for various reasons. That is approximately this frequency of sound or pitch at which you and I as adult people can best hear sound. Okay. Now, in comparison to that, let's go ahead and look at a child. So what would that make a difference for the size of the person? And a child will definitely be a lot smaller than an adult, so let's do the same solution, but for our kid. So for the child, the fundamental wavelength would be 4 multiplied by 1.5 centimeters. And again, I'm just picking some number here to represent a kid. Obviously, children start off much smaller and grow to be much larger. So again, just grabbing a number as a comparison's sake for our purposes here, just to demonstrate how it might work. That, of course, will be 6 centimeters, or 0.060 meters, like that. And then the frequency for our child, this particular child at least, same speed of sound in air, but now divided by 0.06 meters for our fundamental wavelength. And the frequency, notice, will be significantly higher. Which is to say what? Children can hear higher frequencies than adults, or higher pitches than adults. That's really what it says. And more carefully, they're more sensitive to these higher frequencies than we are. So if something is at a higher pitch, it might not be audible to an adult, but it could be heard by a child. Now, by the way, by the same token, it works the other way around. Again, other things being equal, an adult can hear lower pitches than a child can. So, and that's just because of the physics of the situation, the physics of the ear itself. Again, this is not talking about other issues that might be at play with regards to the person or to the physiology. But as far as just straight up physics is concerned, this is a hint as to why we hear the frequencies of sound that we hear. All right. Technical support, as always, is from Sidney Gauchow and Sophia Turner. Funding for this project comes from the University of Mississippi and University of Southern Mississippi. These videos are recorded in Haysburg, Mississippi. I am your host, Dr. Christopher Sorolla. As always, thank you for your attention and clear skies.